So the next lesson in this hyperbolics pack is concerned with inverse hyperbolic functions. It's useful to know what the inverse hyperbolic functions look like on a graph. So for example, if we have f of x equals sine x, then the inverse function f inverse is called r sine x, and it looks like this. So the sine x graph is this one, hopefully highlighted in black. And then if we reflect in the line y equals x, the r sine x graph looks like this. No asymptotes for these ones because it does carry on up to infinity and down to minus infinity. Similarly for r cosh, which is the inverse of cosh x. So the cosh x graph looks like this. Now, usually cosh x is a many-to-one function, like a quadratic. So it's for it to have an inverse, it needs to have a restricted domain so that it's restricted to 1-to-1. So we restrict the cosh x to be just for x is greater than or equal to 0 and y is greater than or equal to 1. That means when we reflect it in the line y equals x, it looks like this, and it's only defined for x is bigger than or equal to 1. Okay. Again, no asymptote unless it does carry on up forever, although my graph doesn't look like it does. Finally, for than x, inverse function we call r than. Than x normally looks like this, with asymptotes at 1 and -1. But if we reflect this in the line y equals x, you end up with this, which looks like just a tan graph. It's already 1-to-1. You don't need to restrict the domain. It just turns out the domain of r than x is between 1 and -1, because that's where the range of than x was. Okay. Your calculator can draw all of these for you, but it's useful to know what they look like. It turns out as well, if we go back to the exponential definitions of hyperbolic functions, we can then rewrite the inverse functions in terms of natural logs. These are given on the formula booklet, so you can just quote these. You don't need to prove them every time. So as some examples, first off, if you are asked for the exact value of r sine 1, use the formula for r sine x, which is the second one here, and just substitute in 1. Obviously, 1 squared plus 1, that gives you 2. So we get ln 1 plus root 2. For our cosh x, the top one, so we're going to substitute in 2 to this one. So ln 2 plus root 2 squared minus 1 rooted. That's the same as ln 2 plus root 3. And r than a third, substituting that into the formula, so that's a half ln 1 plus a third over 1 minus a third. Simplifying this, well, 1 plus a third gives you 4/3. 1 minus a third gives you 2/3. The other 3's cancel. The 4/2 cancels to give you 2. So a half ln 2. Or if you really wanted to, you could take the half up to be a power. Now, it's not often asked in exams, but there is the possibility that you may get asked to prove these formulas. So first off, we'll look at r sine x. And we're going to start off from the definition of sine x in terms of exponentials, which is e to the x minus e to the minus x over 2. We're going to let this equal y. We're going to do what you'd normally do to come up with an inverse function. We're going to rearrange to make x a subject and swap your x's and y's. So if I'm going to times it by 2 first. Give me this. And then I recognize this is kind of a disguised quadratic in e to the x. So if I times everything through by e to the x, which gets rid of the e to the minus x power, and get it all on one side, this is a disguised quadratic in e to the x. To make e to the x a subject, I want to complete the square. So I'm going to complete the square on this. Halving my e to the x term just gives me y squared. I square the y and take it away, and I've got the -1 there as well. I can add that across to the other side. Give e to the x minus y all squared equals y squared plus 1. Now I'm going to square root both sides. And add the y across. Give me this. But I have a plus or minus in here that I don't want. So the argument here is that e to the x is bigger than 0. And if you think about y minus root y squared plus 1, that's going to be less than 0. Y minus root y squared plus 1 is less than 0 because y squared plus 1 is a bit bigger than y squared. If you square root that, it's going to be a bit bigger than y, so it's going to be less than 0. So the only value we have is e to the x equals y plus root y squared plus 1. For the inverse function, I now need to replace the x, swap the x and y's around. Could have done that at the end. And then to get y on its own, I'm going to ln this thing here. Tidy it up with a little as required. Sometimes I like that in it. Doing the same for r cross is a little bit trickier at the end. So the mechanics are all the same. So if we start off with y equals cos x, which is e to the x plus e to the minus x over 2. We're going to do exactly the same thing. So I'm going to whiz through this because we're doing a disguised quadratic in e to the x. So times up by 2 times through by e to the x. Make it a disguised quadratic equal to 0. Complete the square. Take that over to the other side. Square root both sides. And make e to the x a subject. And I'm going to take logs 2. So x equals ln y plus or minus y squared minus 1. And swap the x and y, so y equals ln y x, sorry. Plus or minus root x squared minus 1. But the problem that we have here is we've still got that plus or minus in there. This time it's because of the fact that cos x isn't 1-to-1. So remember what cos x looks like and r cos x looks like. So we restricted the domain so that cos x looked like this one and r cos x looks like this one. So there's some long, complicated arguments that you can make here. You can see in the textbook if you want more details. But the long and short of it is we want the bit of this where this is above the x-axis, where r cos x is above the x-axis, which corresponds to the positive of the plus or minus. I'm not going to go into more detail than that. If you want to, you can look it up. Okay. I'm going to say but. R cos x is bigger than 0, so we want r cos x equals ln x plus root x squared minus 1. The minus would give you the bit underneath the x-axis, which we don't want, otherwise it wouldn't be an inverse function. And this is only true for x bigger than or equal to 1 from that square root there. Otherwise, you'd be square rooting a negative and getting complex. Pause the video and have a go at this U try here. So proving the same result for R pan, and I'll reveal the answer in a minute. The idea for R pan is the same. So substitute any definition for R pan in terms of exponentials. I've swapped the x and y's at the start here. Equally, you can swap them at the end. Remember, you're trying to make y the subject, so I'm going to times up by the denominator, collect all of your x's. So I'm making y the subject. So collect, expand out your x on the left-hand side. Simplify this by timesing through by e to the y, just like we did last time, and then collect your e to the 2 y's up on the left-hand side. Factorizing that out and dividing by the bracket gives you 1 plus x over 1 minus x, and then if you ln both sides and divide by 2, you get the answer that you want. The argument about the asymptotes and stuff at the end, so that fraction inside there, if x is bigger than 1, then the bottom of that fraction is negative, and if x is less than -1, the top of that fraction is negative as well, and the other one's even. Yeah, so, and the other one's positive, sorry. So then you can conclude that this is only valid for modulus of x is in between, modulus of x, sorry, is less than 1.